Welcome to point 6 exponential functions. Exponential function is a function represented by a constant base with a variable exponent. We've got these examples up here. Basic properties of exponents are used when working with functions. And I wish, he's trying to save space on the paper, so he decided to, write some things kind of sideways and then down. This little box is better represented here. I know you guys have seen this, right? And almost everybody does it just like this. And what do these numbers represent? They represent the actual rule as he has it in your book. So if you want to copy that down, or whatever, I'm going to refer to these numbers and be able to talk about the name of the property while I'm using it. But I do like one thing about the book, which is this most important rule right there. Absolutely most important rule. Don't forget that. It's very easy to forget. I call it the zero rule. And I believe they do zero exponent rule. I'm just too lazy to put the word exponent in there. All right, so when simplifying, do not leave answers with negative exponents because you need to practice multiple choice problems. When you're doing free response, it's okay to have a negative exponent, but when you're doing multiple choice, you have to see how they reorganize it. And then the other thing is aren't you glad you had me as a teacher where I made sure that you had this memorized, right? And then I made sure that you had this memorized. Notice this rule right here, radical to rational conversion rule. I write it backwards from this rule on the internet, has it too, a to the m over n equals the nth root of a to the m. That's my internet searching right there. He doesn't have it on here. So if you aren't copying that whole table down, you should copy down just this piece. A to the m over n is equal to the nth root of a to the power of m. All right. Now, simplifying without using a calculator, we do want to be able to do that. And isn't it funny if, you're with me, I make you memorize all of these. Sorry, let me give you the answer key. You want to write these down? Go ahead and write these down. These are all of the potential problems that is going to be on this first unit test. First unit test, so important. There you go. I know, the section where you're not allowed to use a calculator. So I'm throwing it into my OneNote right down here. Okay, there they are. Now, but I'm actually going to do this one for you because, it's in here. So 27 to the 4/3. Ooh, that's a little bit different than what's on that other paper that I showed you. That's because the ones that I showed you are on the unit test, and this one is not. But let's do it. So 27 is the same thing as 3 cubed, and I have a 4/3 power right there. And the way I'm recommending that we do that is we're going to go ahead and use this rule, power of a power rule. It says that if you have these two powers, all you have to do is multiply them together. So that's what I'm going to do. So I'm going to say that we multiply exponents. And I'm writing down what rule I'm using here. Rule was going to be rule 4. And I'm saying I'm multiplying those exponents. So I have 3 times 4/3. This is technically over 1. These guys cancel out. My answer is 4 over 1. 4 over 1, which is equal to 4. So that means that I have, gotten these to simplify down to 3 to the 4th. And aren't you glad I asked you to memorize that? Because take a look at it. It is absolutely on this test. 3 to the 4th was 81. But just in case you do forget what it is, why not do it the long way? We're going to say this is 3 squared, which is 9, and 3 squared, which is 9, because 2 times 2 is 4. 2 plus 2 is 4. And so 9 times 9 is equal to 81. That's how you got that answer. Zero rule. Number 2 is the zero rule. This is rule number 1. He thinks it's so important that you need to know that anything to the 0 power is just 0. I don't have to worry about adding these up first. I don't need to worry about distributing this 0. This whole thing is equal to the 0 power. That's why it's equal to 1. The rules that I would want to use for number 3 are complicated. I mean, I'm pretty sure I'm going to use rule 4. I'm going to use rule 6. Looks like I have a negative exponent here, so I'm going to use rule 7. And honestly, all of those, oh, and golly, don't forget, I'm probably using rule 5 too. So in what order? Maybe you want to stop, pause, try it in whatever order you want, and then just check to see if your answer is the same as mine. Because when you do it my way, which isn't the way that necessarily makes most sense to you, it can be confusing. But I'm going to show you, my steps. I'm going to say that I have e to the 5th, and there's an e to the negative 3. So I'm going to do 5 minus 3 is going to equal 2. So I'm going to say that I have e to the 5th times e to the negative 3 is going to be e squared. And then this thing is all going to be over e to the 4th. And then I still have this 2 on the outside. And notice that this 2 is this 2. And that 2 is purple and this 2 is purple. Now, I'm wanting to let you know that the next rule that I want to use is right here. What rule did I use when I went from this motion right here? I'm saying this is rule 5. And then I want to have e. Do you want to distribute that 2 first? Why not? You know what I mean? So I'm going to say that I have e to the 4th, and then I have e to the 8th. And what was the name of that rule? It was rule 6 when I did that. And then I have oh no, not rule 6, my bad. Rule distributing to, rule 6. Yeah, rule 6. But what do I want to use now? I wanted to use this one, quotient rule. This is rule 3, where I have x minus y is going to be e2 minus 4 is going to end up being e to the negative 2. And then I want to use the negative exponent rule, which is rule 7, says that I have 1 over e to the 2nd power. There you go. How about down here? Notice that 25 is 5 squared, and so I could say that I have 5 cubed, and it's times 5 squared, which is being taken to the negative 2 power. What rule is this going to be? This is rule 4. So I'm going to say I have 5 cubed, and it is times. What do I do with these? Remember, we just multiply, and so I have 5 to the negative 4, because negative 2 times 2 is negative 4. And then I'm going to go ahead right here and use rule, this rule right here, the product rule, which is rule 2. And I'm saying I have 5, 3 minus 4, which is going to be 5 to the negative 1, which is going to be 1 over 5, because I just used the quotient rule. I'm sorry, negative exponent rule right there. This is rule 7. Now, solving this without a calculator, not very hard, but just let me do it in a nice spot right here, okay? 9 to the power of x equals 27. Do you recognize those also powers of 3? So I say I'm going to have 3 squared, which is taken to the x power, and I have 27, which is 3 cubed. Now, what am I doing? Steps. Get the same base. That's a goal. Okay. Now, I asked you to memorize all of those different powers because I want, if you need to take something to a base 2, take it to a base 2. If you need to take something to a base 3, like we did here, you can do that. If it's a base 5, you can do that. You need to be able to recognize all of those powers. Powers, base 10s. We memorized a whole bunch of those so that we could do problems like this. Why? Once we have the same base, just set exponents equal to each other. How come? Well, hold on a second. Let me fix this. This is, what rule is this? This is the rule where I have a power on a power, what was this one called? Power of a power rule. This is rule 4. Rule 4. I'm going to have 3 to the 2x, and that equals 3 cubed. Look, I need to take 3 and cube it, right? And then I need to take 3 to some other power. And whatever I get, it has to be exactly the same thing as 3 to the cube power. So that means I have 2x, and let's do it in this pretty purple, 2x equals cubed. This and this, those are just the exponent. Divide by 2, and I say that I have x equals 3 halves. And you're like, well, I don't know that I get that. Okay, I understand, but here's the deal. If I put a 3 halves out here, then 3 halves times 2 is just going to be 3, which is going to make it match that, right? So 3, check your work. This is going to be 3 squared times 3 halves. Is that equal to, question mark, 3 cubed? Well, yeah, because 2 times 3 halves is, ready, just 3. So 3 cubed, does it equal 3 cubed? Check. It totally does. Okay, so now we want to use a calculator to do some graphing, and it's 2 to the x, 5 to the x, and e to the x. And don't forget that e to the x is a function that you have learned, all right? You definitely have. So I have 2 to the power of x, and that's my first one. Hit tab. Oh, I'm in, wait, oh, sorry, double check. Look, I graphed a constant. I got whatever 2 to the second power is, which I guess is 4, right? I meant to put in a variable there. Ta-da! There's 2 to the power of x. And then hit tab again. Did you see? I hit tab. That's how you know I hit tab. It's because of that little red button right there. Every time I hit a button, it's red over here. So then I'm saying that I have 5 to the power of x. And then I'm going to hit tab one more time, and that is going to be E. But don't just type E down there. That's not the right E. This is the right E, or you can go in here, and that is the right E. But I actually wanted to put it to a power, so this is the best button for that. All right, E to the power of x, boom. And now you can see those 3 functions. And which one is growing faster, by the way? Which function is growing faster? It's the red one. The red one has a taller height than any of the others. The red one has a taller height than any of the others. So I just want to be able to write on this graph. So I'm putting it over here. And ta-da. This is what I would do with that. Oh, it's awfully big. So take a look at my height at 1. If I draw a straight line at 1, this one is around here, which is, sorry, my bad, which is around here. That's e to the x, so this is going to be e, which we remember as being approximately equal to 2.7. I think there's more digits that I don't keep in my head. This, notice that it's at a height of 2, and this, we notice, is at a height of 5. 1, 2, 3, 4, and 5 is at a height of 5. So this one grows faster. Well, makes sense. I'm taking a bigger number to a bigger power, just so you know. And then when we do the little graph here, what we noticed was we had this 1, we had this 2.7, and we had this 5. And did you also notice that every single one of these guys, let's take a look at this, every single one of these guys crossed at this moment right here. And why is that? Well, because anything to the 0 power is equal to 1. So here we go. This guy was 2 to the x, and this guy was e to the x, and this one more color. This guy was 5 to the x. And don't make fun of me down here. These lines are supposed to literally touch very, very close. Because remember that it's asymptotic. Asymptotes at y equals 0 for all of them. How come? Well, because there's nothing being added or subtracted at the end. If I had, a plus 3 here, the asymptote would be a 3. If I had a plus 10 here, the asymptote would be a 10. On any one of these, whatever number we're adding, that is going to be our asymptote. And notice, he says write that for you exactly anywhere. But I'm going to do that for you. We're going to talk about exponential functions in their format here in just a second. But what he does talk about is really important. Notice that he's saying that a is greater than 1, that these graphs of exponential functions, that's when a is bigger than 1. So the words that go to this, when the base is bigger than 1. Okay, and then in that case, these are growth equations now, because a is bigger than 1. It also has some language which you need to really get familiar with and make sure that you understand. We have talked about continuity. Is the function something that you can draw with a pencil without lifting it up? Meaning that it's not asymptotic in a way that there's pieces of the function that do different behaviors. All right. Also, I want to add the word strictly, and I'm going to make it in red because it's that important. Strictly increasing. Strictly increasing means never has a moment where outputs go down. Concave upward, if you want to talk about concave up, which I think I have mentioned before, concave up looks like this or like that, and sometimes the two of them will come together. Concave down looks like this or looks like that, and sometimes it comes together like this. I meant to reverse where these were. Concave up looks like this. Concave up looks like that. And I know when you draw this, you're thinking, but aren't I going down? Sure, but it's half of a cup. Here's my cup. Concave up means a cup. And concave down means a hill. All right. And so even the half by itself, this half is strictly going down. This half is also strictly going down. All right. Letter E is used as a base in these examples, and it's not an unknown. And, oh, well, hold on. Right there, limits taught you this. Remember, we talked about the fact that when we're going to the left, that's where the limit is equal to 0. And when we're going to the right, that's when the limit is equal to infinity. And aren't you glad that I've already explained this to you? Because he says in his book, he's like, this notation using limits will be developed completely in the next unit. He's going to check to see whether or not you know anything about limits so that he can kind of coach you as you move forward in the class. I've already made sure that everybody who's in this class should have learned a little bit about limits. The y-intercept is at 0, 1, always y. Anything, well, yeah, why not? Why not? You could just call it the 0 rule. Anything to the 0 power is 1. And another key point then that you could say is that you end up getting 1 and a, which we already talked about. Whatever a is, we get that point, and that's how we graph these anyways. Now, notice that he told you nothing about decay equations. So do you want to talk about decay equations just a little bit? Decay equations occurs when a is between 0 and 1. Meaning like a is a half or 2/3 or 4/5 is whatever. It's a decimal. If a is a fraction or a decimal, a fraction less than 1. Because 1 and 1/3, right, 4/3, that would be bigger than 1. So we just want to say if it's between, and it doesn't have the same shape. Okay, instead it'll have this shape. So it's still concave up, but now I can say that the function is strictly decreasing. And I can also say that I know that the limit has flipped. When x is going to infinity now of this function, then I would say that I'm going to get my asymptote value, and that's in this direction. In this direction, meaning that I'm still going out on the x-axis and I'm tracing up to how high I'm getting. I'm going out on the x-axis and I'm tracing out to my infinite behavior right here, where it's going bigger and bigger and bigger. I know it grows so fast that you feel like it just goes straight up, but it's just, you have to kind of like zoom out, and once you zoom out, you're like, oh yeah, no, eventually it is going to reach over here. As x gets bigger, y is getting bigger, means that I have ready the limit of f of x as x approaches negative infinity will be positive infinity. So, those are some things that key intercept is still going to be the y-intercept is still going to be 0, 1, and another key point is still 1 over a. That still occurs, okay? And the domain of this is still negative infinity, positive infinity, and the range is still restricted to being not able to be equal to 0 and going up to infinity. So there you go. I will also like to talk about kind of translations with values of e in just with exponential functions in just a moment. Let's go ahead and talk about e. I taught it to you as being continuous. E is continuous compounding of our $1 interest with 100% only $1 principal with 100% interest. And do you remember that? Where it was like, oh, well, let's compound it twice. What do we get? Oh, let's compound it 8 times. What do we get? Let's compound it every month. Okay, let's compound it every week. Let's compound it every day. Let's compound it every hour. Let's compound it every second. Do you remember that? And the number that we got was that if you took that dollar and you did that, compounding it basically every second continuously, every second, or fraction of seconds, what we got was $2.71, which we don't round up to $2.72. No, we don't. We use 2.718. Okay. Right here, yeah, 2.7 something. Isn't that what I said? Good. I just have a hard time remembering that. 718. Okay, so sketch that graph here, and the asymptote going to 0 out there in the negative direction, and here's what we've got. Now we want to talk about adjustments to the graph, okay, without using a calculator? Sure. So just a little bit of a moment here. So I'm going to say that I could write an exponential function like this. I know he says a is the base, and I'm sorry, but I'm used to having b be the base. And I say this is my exponent, and then what if I did something to that exponent? And right here, what if I did something to the whole thing at the end? Do you recognize the h and k? H and k are not vertices here, okay? K is not a vertex, but the same translations apply. B is the base, A is a multiplier. What does A do? Well, if A is positive, then it is going to be concave up. Which, remember when I was doing, back in the day, you do quadratics. You're like, oh, it's a happy parabola. This is like a happy exponential. If A is negative, then it is concave down. And then if it's a multiplier, if it's bigger than 1, it can be a vertical stretch / compress. Then H, if it is positive, it means that it is a shift left, and if it is negative, then it is a shift right, and if there is a K, then it is a shift up. If you see a positive, and it is a shift down if it is a negative. And now you see me talk about this with every single different kind of function, okay? So if I take this guy, and I just wanted to do e to the x, remember e to the x would be this guy right here, e to the x, right? Maybe I could make it grow a little bit quicker down there. And I'm saying if I wanted to do, if I wanted to do e to the +1, well, what do? I take this and I shift it up 1. Ready? Boom. I shifted it up 1. And that's it. Okay. Like, wait a minute. It used to cross right here. Now it's going to cross right there. Well, why? Because I wanted to take every output and make it 1 bigger than it was before. Then I wanted to do some kind of thing to it right here. And you might be wondering to yourself, what exactly are we doing when we do this? Well, I mentioned H, and there's no H here. So this -1 is not H. What this represents is actually some kind of reflecting of the X values. Okay, some sort of reflecting of the X values. And I in fact, not reflecting, let's say reciprocating. Okay, reciprocating, because I'm going to start graphing something that looks like this: 1 over e to the x. That's the negative exponent rule. Exponent rule. And you're like, ooh, I still not sure what that is going to mean. Well, I tell you what, it means that I have some kind of reflecting of values going on. Let's break it down. If I have my input is x, and if I have e to the negative x, let's talk about e to the positive x. I was going to say that if I throw in a 0, this is x and this is e to the x, then I have 1. And if I have 1, then I'm going to have e to the first power, which is approximately 2.71. Okay, 8. But what would happen if I had a -1? I would have had e to the -1, which is going to be 1 over e, which is essentially going to be, ready, 1 over 2.718, which is around, if I'm graphing, it's around 1/3. So when I was looking at this function before I shifted it up, and I was graphing it like, I want to hit here. I want to hit here. Boom. Originally, I was looking at this function. I was trying to make sure that I was down here around, ready, approximately equal to 1/3. I graphed that. I graphed this point. Okay. Then I shifted it up. Yes. So this is e to the x plus 1. And this is just e to the x. Some sort of artifact there. Okay. So now, none of these are the graph that I've been asked to graph, Ms. Shatra. I know, but here, let me just hear me out. Notice how I got this -1. I'm going to throw in 1/3. Well, what happens if I take the negative of x? All right, let's try that. So I have 0. This is e to the -0, which is going to be what? E to the 0, which is still just 1. That didn't change at all. What about this? Is this going to change? Well, this is e to the negative of -1. Notice I have a negative sign here out in front, and that is that negative sign, and I have this negative sign, which is my input. So that's how come I have 2 negative signs. And guess what? That means I have e to the first power, which is approximately equal to 2.718. What do you think now is going to happen right here? Yes, it is going to flip these two values. They're basically going to go to a different spot. It's just, like I said, some kind of reciprocating. So we have e to the -1 power, which is really 1 over e, which is approximately 1 over 2.718, which is super duper close to 1/3 if you're graphing. Now, don't do this on the AP exam because, don't write that ever. Don't write that ever because it's not really true. On the AP exam, you need to be 3 decimal places of accuracy, and this is 3 decimal places of accuracy. But just for the purposes of graphing, can I graph it? Okay, so now I'm doing all of this in orange. Okay, I'm going to do all of this in orange. I still hit this point. I guess I should have done it in blue. There was a blue dot there. And guess what? When I'm at 1, I'm at 1/3. And when I'm at -1, I'm at 2/3. And so guess what this means? It is a reflection. Ready? This is a reflection across the y-axis. So the graph is a reflection across the x-axis. Y-axis, my bad. Y-axis. And notice it is also now a decay function. Now it is a decay function. And guess what? I forgot to shift it up 1. I'm going to take it. Oh boy. Well, I'm going to get rid of that because it's going to make it impossible for me to shift it up 1. Ready? I have to shift it. Oh, yeah. I'm not going to be able to shift it like that. I'm just going to have to move every value up 1. Up 1, up 1, and up 1. And this, and it is growing faster. This is e to the negative x plus 1, and this one was e to the negative x. There you go. I graphed more than he wanted me to, and I'm sorry if that bothered you. Go ahead and get good luck. Get to work on that practice.